Hello there, this is a geometry video and it is chapter 7 sections 1 and 2 today. We will be talking about ratios, proportions, and then how they relate to similar polygons. Now first I want to just give you the definition of a ratio. A ratio is a comparison of two quantities using division. A lot of times you hear these types of ratios on TV, actually in commercials. You've probably heard things like 9 out of 10 dentists agree. That's a ratio because they're talking about the number 9 and the number 10 both refer to the same thing, dentists, 9 dentists out of 10 dentists. As opposed to a rate, for example, when you say something like 25 miles per hour, it's 25 to 1, so it's 25 miles and then 1 hour. And so the two numbers are not the same, they're not measured in the same unit. Miles and hours are not measured in the same unit. But when you have a ratio, when you compare those two quantities using division, you're using the same unit, miles to miles, hours to hours, dentist to dentist, and so on and so forth. There's a couple of different ways that you can express a ratio. You can actually write it out A to B with the word 2 in the middle there. You can use a semicolon. Actually, that's actually a colon. A semicolon has a little comma, right? So you can use a colon, or of course you can use a fraction. Of course, we want to make sure that the bottom of the fraction, which is the B, is never equal to 0 because we don't want to have division by 0. And so that's basically a ratio for you. So we're going to have our first example here. It's real basic and straightforward. A baseball player's batting average is the ratio of the number of base hits to the number of at-bats. Hi, buddy. Bye, buddy. Sorry about that. Anywho, so not including walks. So the Minnesota Twins' Joe Mauer, I'm not even sure I'm saying that right, but for all of you baseball fans out there, don't shoot me. But this Minnesota Twins player had the highest batting average in Major League Baseball in the year 2006. If he had 521 official at-bats and 181 hits, find his batting average. So we know from the earlier part of the question that the ratio is the number of base hits. So we want base hits compared to the number of at-bats. And that's not including walks. Okay? So then, further on, we read that he had 521 official at-bats. That number goes in the bottom. And 181 hits. So all we have to do is take 181 and divide it by 521. And we get approximately 0.347. 0.347. So that is apparently Joe Mauer's batting average, 0.347. Apparently that's pretty good. I don't know, I don't play baseball, but there you go. So now I would like you to try this do-it-yourself question number 1 here, and then we're going to move on to extended ratios, because believe it or not, you can extend a ratio. Basically, an extended ratio just means that you are now comparing, instead of just two quantities, 3 or more quantities. And that's what an extended ratio is, but it doesn't really change much of what we're doing. You can just compare 3 or more quantities at the same time. So as before we had like A to B, we have now A to B to C. So there's actually 3 quantities being compared, but that's okay. I'm going to show you how to do that in this example. The ratio of the measures of the angles in a triangle is 3, 4, 5. Find the measures of the angles. So basically the ratio being 3, 4, 5, just simply, it doesn't tell us that the side lengths are 3, 4, and 5. It tells us that the ratio of one side to the other is 3 over 4 and then 4 over 5 and so on. So actually, this is actually really simple to do. We don't know the actual measure of the angle, so we're going to go ahead and call that x. And what you want to do when you have your ratio amounts like that is basically just, I'm going to try to find the smallest angle here. We're going to call this 3x. And then this is probably the biggest angle. We're going to call that one 5x. And this is probably second to the biggest, 4x. And you don't have to necessarily draw the diagram. I just drew it so that you can see it better, understand what's happening here. We don't know what the actual angle measure is, but we know that whatever it is, we're going to times it by 3 and 4 and 5 in order to get that ratio of 3, 4, 5. So we have 3x, 4x, and 5x as our angle measures. And since we know from before that the angles in a triangle all have to add up to 180, all we're going to do now is take the 3x plus the 4x plus the 5x and equate it to 180 because we know the triangle has 180 degrees total. And so once you've done that, it basically just becomes an algebra problem. 5 plus 4 is 9, and 9 plus 3 is 12, so this is 12x equals 180. Then we divide by 12 on both sides, and we find out that x actually equals 180 divided by 12, 15. And it says to find the measures of the angle. So even though we found the value of x, we still haven't found the actual angle measures. So now you want to find all three angle measures. So we're going to take 3 times 15 is going to give you 45 degrees. So we have a 45 degree angle. We have 4 times 15, which is going to give us 60 degrees. And then we have 5 times 15, which is going to give us 75 degrees. So our three angle measures are 45, 60, and 75, and they all add up to 180, so that would make sense. All right, so now we're going to go and let you do this do-it-yourself question, and then we're going to talk about proportions. Now, proportion is basically when you equate two ratios. So we already talked about what a ratio is. So a proportion is an equation that states that two ratios are equal. So we have here basically what that would look like, the ratio of A to B and the ratio of C to D, and now they're equal to each other. When that happens, we can solve for one of the quantities by using the cross product property, and we did this in Algebra 1. So just to remind you what that means, A and D are what we call the extremes, and that's why I've kind of color-coded them red. And B and C are what we call the means, all right? So the cross product property tells us that the product of the extremes, which is A and D, equals the product of the means, which is B and C. So basically you have that if you have A to B equals C to D, then A times D equals B times C. Or in other words, you take the cross product. That's what we call the cross product, because you have this little cross going on here, and of course you're multiplying A times D. So we're going to use that here to solve these proportions in example 3. So we have here, the first one is actually very, very straightforward. It's not until we get to part B that it kind of gets interesting. But we basically have a cross product, so we're going to say 21 times x is 21x, and that's going to equal the extremes, which is 6 times 31.5, which is 189. Then divide by 21 on both sides. So 189 divided by 21 is going to give you 9. So x equals 9. Now, in part B, we want to be really careful that when you have a binomial like this on top of a fraction, or on the bottom, which you have in part B here, and even in part C over here, you have to be really careful that when you do the cross product, that you use parentheses. So you want to go 5 times x plus 3, the whole quantity of x is 3, equal to 4x times 2, which is 8x. All right, so it's important that when you have a binomial that you use parentheses, because you have to distribute the 5 to both the x and the 3. So we're going to get 5x plus 15 equals 8x. And when people don't distribute that 5 to the 3, then that's when you oftentimes get the wrong answer. So to combine our like terms, we're going to bring these 5x's to the other side of the other 8x's. And that's going to give us 15 equals 8 minus 5 is 3. And when we divide both sides by 3, we get that x equals 5. All right, so in part A, we got that x equaled 9, and in part B, we get that x equals 5. So now I'll have you try do yourself number 3, A, B, and C. Okay, in example 4, we're going to use proportions to actually predict, okay, when we don't know something. So it's going to be really simple and straightforward here as well. It says Fernando conducted a survey of 50 students driving to school and found that 28 of those students owned cars. If 755 students drive to his school, predict the total number of students who own cars. So basically he has a small sampling of 50 people compared to the entire school population, which is 755 of students that drive to school. So out of the 50 that he surveyed, 28 owned cars. So we know that 28 owned cars out of the 50. Now, assuming that this same ratio is present in the total population, then we're doing the same thing. We have the amount of owned cars versus the amount that were surveyed. So in this case, we have the amount of owned cars, which is what we don't know. It says to predict the total number of students who own cars. So we don't know how many own cars when we talk about the entire population, which is 755. Okay, so out of his survey, he had a smaller population of only 50 students, and out of those 50, 28 owned cars. So we're basically saying how many owned cars to the population. And now we want how many owned cars, which we don't know, compared to the population, which of the entire school is 755. So now, that's how you set it up, and then we're going to go ahead and use cross products to solve. So we're going to get 50x equals 28 times 755, which is 21,140. We take that and divide it by 50, and we get 422.8. All right, now we know that we're talking about actual people here, so we don't want to say 0.8 people, because that would be like, I don't know, 422 people, then the 423rd person would have some limbs chopped off or something, because it wouldn't be a full person, it'd be 0.8. So we don't want to do that. So, and I'm sorry for being a little graphic there for you, but we're going to round this to a nice round integer. So we're just going to round it up to 423. Okay? So out of the 755 students that drive to school out of this high school, 423 of those own their cars. So we're going to have you now do something similar with this example here. This is biology experiment here. And then we're going to actually move on. That kind of pretty much concludes 7.1. And then we're going to go on to 7.2 and see how these proportions can help us with similar polygons. But before we can talk about the proportions in similar polygons, we have to actually know what a similar polygon is. So similar polygons are basically polygons that have the same shape, but not necessarily the same size. Okay, and we have a symbol for similarity. We use this just the one squiggly as opposed to two squigglies. Two squigglies would be approximately. Obviously, two squigglies and a dash are the congruent symbol, so we don't want to do that either. So a similarity statement is when you just have the one squiggly. And I'm pretty sure that it's not called a squiggly, but that's just what we're going to call it because that's what it looks like. All right, so anywho, we have here basically some a diagram to help you understand how this works. So two polygons are similar if and only if their corresponding angles are congruent and corresponding side lengths proportional. Notice that it doesn't say congruent in both places. The angles have to be congruent, but the side lengths have to be proportional. And we just talked about what a proportion was. It means that when you have those two, the ratio of the sides has to always be the same, proportional, okay? So basically, we have a diagram over here of a quadrilateral. We have A, B, C, D, W, X, Y, Z. It's all color-coded for you. So we have that angle A is congruent to angle W, and you can see that because they each have only one arc. And then B and X, the red angles, have two arcs, so those are congruent. And then angle C and angle Y with three arcs, and then finally angle D and angle Z with four arcs. Furthermore, we have the corresponding side lengths. So we have AB, again, color-coded with WX, so that's 15 to 5, and 15 to 5 is a ratio of 3 to 1. And then we have BC to XY, and that's 12 to 4, and again, the ratio of 12 to 4 is 3 to 1, because 12 divided by 4 is 3. Then we have from CD to YZ is our third pair of sides, and that's going to be from 21 to 7. So again, the ratio of 21 to 7 is 3 to 1. And then lastly, we have DA and ZW is our last pair of sides, and that ratio is 18 to 6. And again, the ratio of 18 to 6 is 3 to 1. And so you can see here that all of these corresponding side lengths are proportional. They all have the same ratio, which is 3 to 1. So when that happens, you can say that the two polygons are similar, and when you say that they're similar, this is what we call a similarity statement, where you actually state that they're similar. And when you do that, just like before with the congruent triangles, the letters have to be in the right corresponding order. So A corresponds with W, B corresponds with X, C corresponds with Y, D corresponds with Z, and they're in the same order. And that's important. So if you put them in the wrong order, then it would be wrong. So then we have an example for you. We're going to continue with example. In the book, it's not considered example 5. It's example 1 of 7.2. But since we're continuing from the previous, we're going to call it 5. So it says, if triangle FGH is congruent to JKL, list all pairs of congruent angles and write a proportion that relates the corresponding sides. So now in this case, this is why it's very, very important that you always have the letters in the right order, because you might not be able to tell from the diagram which angle corresponds with which, but you can always be safe when you're using the actual position of the letters. Because these are written in the right order, then I know that F corresponds to J, because F is in the first position here and J is in the first position here. So as far as list all pairs of congruent angles, I know that angle F is congruent to angle J, and because G is in the middle spot and K is in the middle spot, angle G corresponds with angle K. And then lastly, H corresponds with L, because they're in the third position in the statement, in the similarity statement. So that's really important. And see, if you didn't have it in the right order, we wouldn't be able to do that. But we know that when we write a similarity statement, they're always in the correct order. So that would mean that those are the pairs of congruent angles. And then write a proportion that relates to the corresponding sides. Now right now, we don't actually have numbers for the amounts or what each length is, but we can still write the proportion, because we can write the corresponding sides. And again, it's going to be very helpful to you when you write the corresponding sides to have them, to base it off of this, as opposed to the diagram, because the diagram can sometimes be misleading. So we know that F, for example, corresponds to J, and then so this triangle is kind of flipped around. So it's a lot easier if you just base it off of the actual similarity statement. So I'm going to say FG, that's one side length. FG is going to correspond to JK. And the ratio of those two sides should compare to, for example, GH. And GH is going to correspond with KL. And lastly, our last side, so you can see from here that we have FG, GH, now we want FH, or you could call it HF. I'll go ahead and call it HF. And then this will be LJ. Okay? And so that would be my proportion that's relating my corresponding sides. All right? FGJK, GH, and KL, and then HF and LJ. And again, you can see those from the diagram, but I think it's a lot easier to base it off of the similarity statement. So you can do whichever way is easier for you. So here we have do it yourself number 5, where you can attempt to do that on your own. Again, be careful that the diagrams are not, they're kind of switched around. So again, it's a lot easier to base it off of the similarity statement, but you do as you will. All right, so example 6. In example 6, we have something that they're asking us to find here. It is called a scale factor. A scale factor is basically the proportion of the sides. Earlier we saw that in the first example, we saw that the ratio or the proportion was 3 to 1. And that happened here. We did the ratio here of the proportion, and it was 3 to 1. That's basically what we call a scale factor. However, sometimes you can have, going back to here, the scale factor can be different if it asks you to write the factor going from this figure to that figure. So I went 15 to 5. So I put AB on top and WX on bottom. So all of them were from the bigger figure to the smaller figure, and therefore the ratio was 3 to 1, 3 being a bigger number than 1 because this figure was bigger. But also I could have written the proportion backwards, and I could have gone from the smaller figure to the bigger figure, and then it would have been 5 to 15 or 1/3. So sometimes the scale factor can be different based on the order in which you're writing it. So are you going from big to large, or from big to small, or small to big? And so just be careful with that. When it asks you to find the scale factor, you generally want to go from the first figure to the second figure. It doesn't really matter which one's bigger, but you want to go from first to second, unless they specifically tell you to do something different. Okay, so here it says in example 6, determine whether the following rectangular images are similar. If so, write the similarity statement and the scale factor. Explain your reasoning. Okay, so we're gonna basically what's happening here is this is one of the word columns in your textbook, and they're talking about Kuma wants to use the rectangular photo shown. So this is not you don't see the actual photo in your textbook. It's a photo of a dog. Okay, but this is the photo as the background for her computer's desktop, but she wants to resize it. So they're asking us to determine which of these resized options is going to be similar to the original. All right, so we have here 8 to 12 and 10 to 14. So that's what we want to look at. It's going to be similar if the proportion of the sides is the same. So because this is a rectangle, this side is 8 inches, this side is also 8 inches. So whatever ratio I get for this pair of sides, it'll be the same for this pair of sides. And the same is true for AB and EF, and for DC and HG. So instead of doing this 4 times, I'm only going to do it twice because it's going to repeat itself. So basically we're looking for the ratio of 8 inches to 12 inches. And that's going to be, we know that 4 goes into 8 3 times, and 4 goes into 12 4 times. Sorry, I just did that backwards. Four goes into 8 2 times, and 4 goes into 12 3 times. So we get a ratio of 2/3, 2 to 3. And then when I try it with the 10, I get 10 is to 14. And in this case, 2 goes into 10 5 times, and 2 goes into 14 7 times. But the ratio of 2/3 and 5/7 is not the same. So therefore, these are not similar. So for part A, it would not be similar. And if you wanted to explain your reasoning, it would be because they don't have the same ratio. So the sides are not, the corresponding sides are not proportional. All right. But all of the angles, because by the way, and I kind of skipped that earlier, since all 3 of these diagrams are rectangles, we can assume that they're all going to have 90-degree angles. And so all of the corresponding angles are congruent. So from this to A, they're all the congruent angles are there. In part B, the congruent angles are there. The only thing in question is the sides. Okay, so for part B, we try the same thing again. We're going to say 8 to 12, which we already know from before is 2 to 3. And then we're going to try to go from 10 to 15. And this time, 5 does go into 10 2 times, and 5 goes into 15 3 times. So now they do share the same ratio for the corresponding sides. So these side lengths are proportional, and since all of the angles are congruent, then these are similar. Yes, similar. All right, now it says that once you've determined whether they're similar, it says to write a similarity statement. So to write the similarity statement, we write that A, B, C, D is similar, and they have to be in the same order, and we're going to go J, K, L, M, and the scale factor is 2/3. But notice that if I had gone from the larger figure to the smaller figure, the scale factor would be 3/2. Okay, but again, you always want to go from the first to the second, unless it specifically tells you to go from smaller to bigger or bigger to smaller. All right, but in this case, they didn't, so we're going to go with first to second, so we're going to get 2/3. All right, so now we're going to have you try this little guy, and then we're going to go on to finding or using some more proportions, finding some missing variables, if you will. Alrighty then, and we are almost done here. It says in the diagram, which is right over there on the right, ACDF is similar to VWYZ. Okay, and again, you look at the diagram and here's like ACDF, but then it's like VWYZ, so it's kind of inverted and all this nonsense. So it's kind of hard to see sometimes when you're looking at the diagram, but it's actually easier to base it off of the similarity statement. We know that A corresponds to V, C corresponds to W, D corresponds to Y, and F corresponds to Z. Similarly, we know that AC corresponds to VW, DF to YZ, AF to VZ, and CD to WY. But it wants us to find X. So I'm looking over here and I see that X is basically FD. All right, so FD is right here, FD. FD is going to correspond, FD corresponds to ZY. Okay, and then we're going to have, we know that CD is 9, so, and where's WY? And see, WY is 6. So I know that CD is 9, so CD is right here, and it's going to correspond to WY. All right, now there's a reason, in case you're wondering, there's a very good reason why I am using the letters here to tell me which portions are corresponding, so that I can fill in what I know and solve for the missing variable. So in other words, what is FD? FD is X. What is ZY? 10. What is CD? 9. What is WY? 6. So see, now that I've done that, I can solve very simply. 6x equals 9 times 10 is 90. Divide by 6. 90 divided by 6 is going to be 15. So x equals 15. Now, it doesn't have to be the only way that you can set up the problem, but it does help to be able to set up the corresponding side links. So find y, same idea, okay? So y we have right here is VZ. So I got to figure out what corresponds to VZ in the other figure. So here is V and Z, first and last. So it's going to correspond to A and F. Okay, but we also need another pair of segments to use. So I'm going to go ahead and go with AF. AF. Okay, and since A and F are here, oh, sorry, we did AF. My bad. We're going to use the same one that we used in the previous problem, which is that CD is 9. And so that's going to go up here. Oops. CD is 9, and then WY. All right. So we have that. So now we're going to plug in what we know. So VZ we know is 3y minus 1. AF is 12. Okay, so here we have AF is 12. And then we already knew from before that CD was 9. Again, you can still see it from the diagram. And WY was 6. Now this is a case of, like we saw earlier, where you have a binomial, so you want to be really careful that you go 6 times 3y minus 1. You want to make sure that you distribute that 6 to both the 3y and the 1. 12 times 9 is going to give us 108. So we're going to get 6 times 3 is 18y. 6 times negative 1 is negative 6. We're going to move this 6 to the other side. So we're going to get 18y equals 114. And then we're going to divide that by 18.